Hey fellow nerds, today we will solve gate problems on MOSFET circuits from 2015 to 2020. In part 1 of this video, we already solved problems from 2020 to 2024. This is our first problem. An enhancement MOSFET of threshold voltage 3 volt is being used in the sample and hold circuit that is given. Assume that the substrate of the MOS device is connected to minus 10 volt. The input voltage V1 lies between plus and minus 10 volt. What we have to find out is the minimum and the maximum values of Vg required for the proper sampling and holding. First, let me explain to you how a sample and hold circuit works. In the given circuit, input is given at the drain, output is taken from the source. It is also given that the input ranges between plus and minus 10 volt. Let us take a sine wave of 10 volt peak voltage as an example. It ranges from 10 volt to minus 10 volt. Now at the gate of the MOSFET we are giving pulses. When the pulse is high, MOSFET will be on. When pulse is low, MOSFET will be off. When the MOSFET is on, current will flow like this and it will charge the capacitor. So we'll get an output that is equal to the input. That will give us an output signal. When MOSFET is off, current will stop flowing, but the capacitor is already charged from the sampling part. In that case, the output will become a constant. It will be equal to the potential dropped across the capacitor. For example, let us say the MOSFET is on from 0 up to this much of the time. When MOSFET is on, the input is sampled and we'll get an output like this. But when the input reaches over here, MOSFET switches off, but the capacitor has already charged up to a voltage of this much. That means once the MOSFET is off, the capacitor will still have a potential that is equal to this much. So our output will be constantly like this. So whenever the MOSFET is on, it has to sample the input. And when it becomes off, it has to hold the last sampled value. So this is the basic idea. When the MOSFET is on, it should be able to sample the entire signal. That means if the MOSFET is on, it should be on for the entire signal. And if it is off, it should be off for the entire signal. Let us start with the condition for sampling. For sampling, the MOSFET should be on for the entire signal. The condition for the MOSFET to be on is that VGS should be greater than the threshold voltage. VGS is VG minus VS. So VG minus VS should be greater than the threshold voltage for the entire signal. Even when the input has its maximum value. Even when Vx takes the maximum value and Vg minus Vx takes the minimum value, it should still be greater than the threshold voltage so that sampling can be perfect. Or we can write Vg should be greater than Vt plus Vs. Here Vs is the output and the output follows the input. So for the maximum value of Vs, we can take the maximum value of the input, which is 10 volt. It is also given that the threshold voltage is 3 volt. So Vg should be greater than 3 plus 10, that is 13 volt. So the maximum value required for gate voltage is 13 volt. Now let us take the condition for holding. For holding, the MOSFET should be off for the entire signal. And the condition for the MOSFET to be off is that VGS should be less than the threshold voltage. VGS is Vg minus Vs. So we can write Vg minus Vs should be less than the threshold voltage, even when Vs takes the minimum value. Here the minimum value of Vs will be minus 10. So if you take Vg minus minus 10, it will become Vg plus 10, which will be the maximum value Vg minus Vs can take. Even then, it should be less than the threshold voltage so that the MOSFET is off. So Vg minus Vs should be less than Vt even when Vs takes its minimum value, which is minus 10 volt. So we can write Vg should be less than Vt plus Vs. Vt is 3 volt, Vs is minus 10 volt. So gate voltage should be less than 3 minus 10 or minus 7 volt. So this is the minimum value required for gate voltage. Option C is the correct answer. Let us see the next problem. In the given circuit, the W by L value for M2 is twice that for M1. Otherwise, they are identical. The threshold voltage for both transistors is 1 volt. It is also given that VGS for M2 must be greater than 1 volt. Now, current through the NMOS transistors is modeled like this. For VDS being less than or equal to VGS minus VT, that is when the MOSFET is in the linear region, this is how the drain current is defined as. When VDS is greater than or equal to VGS minus VT, which means the MOSFET is in saturation region, this is how we define the drain current. What we have to find out is the voltage in volts accurate to the 2 decimal places at Vx, which is over here. Let's see how we can solve this. The first thing we have to do is find out if these transistors are operating in the linear region or the saturation region. Let us take M2 first. We'll find the value of VGS minus VTH. For M2, the gate voltage is 2 volt. Source voltage is Vx. So VGS will be 2 minus Vx. It is given in the question threshold voltage is 1. So VGS minus VTH will be 2 minus Vx minus 1, which is 1 minus Vx. Let's also find VDS for MOSFET 2. Here the drain voltage is 3.3. Source voltage is Vx. So VDS, which is VD minus Vx, is 3.3 minus Vx. Let us take M1 now and find VGS minus VTH. For M1, gate voltage is 2 volt. Source voltage is 0. So VGS is 2 minus 0 or 2. It is already given threshold voltage is 1. So VGS minus VTH is 2 minus 1 or 1 volt. What will be VDS? Here the drain voltage is Vx, source voltage is 0. So VDS is Vx minus 0 or Vx. So these are the conditions. Let us try to figure out whether M2 is operating in the saturation region or the linear region. In the case of M2, we found that VGS minus the threshold voltage is 1 minus Vx. Also, VDS is 3.3 minus Vx. Obviously, 3.3 minus Vx is larger than 1 minus Vx. So for M2, VDS is greater than VGS minus VT, and that means M2 is in the saturation region. Now, for M1, VGS minus VTH is 1 volt, VDS is Vx. So there is no way we can conclusively say that VDS is greater than VGS minus VTH because we don't know the value of Vx yet. So let us make an assumption. Assume that M1 is in saturation. Now drain current of M2 flows like this. Drain current of M1 flows like this. That means technically drain current of M2 is equal to drain current of M1. Let us write ID1 is equal to ID2. We already know M2 is in saturation. So for ID2, we can use the expression for drain current of a MOSFET in saturation. We are assuming M1 is in saturation. So there also we'll use the same expression. Here Kn is the constant mu n Cox W by L. Half and half can be cancelled. Kn1 multiplied by VGS minus VT of MOSFET 1 squared is equal to Kn2 multiplied by VGS minus VT of MOSFET 2 squared. Here Kn is mu n Cox W by L. Now mu n Cox is the same for both transistors, but W by L is double for M2 when compared with M1. So Kn2 will be 2 times Kn1. So we can write Kn1 multiplied by VGS minus VT of the first MOSFET squared is equal to 2 Kn1 multiplied by VGS minus VT of the second MOSFET squared. Kn1 and Kn1 gets cancelled. VGS minus VT for the first MOSFET is 1 volt. VGS minus VT for the second MOSFET is 1 minus Vx. So we get 1 square is 2 times 1 minus Vx squared, or 1 is root 2 times 1 minus Vx. This gives us the value of Vx. It is 1 minus 1 by root 2, or 0.29 volt. Let us assume Vx is 0.29 volt and verify the conditions for M1. We found that VGS minus VT for the first MOSFET is 1 volt. Now, what will be VDS? VDS is Vx. So, if Vx is 0.29 volt, then VDS will be 0.29 volt. But that means VDS is less than VGS minus VT, which is 1 volt. If VDS is less than VGS minus VT, then MOSFET 1 is in linear region. But we started with the assumption that it is in saturation region. And our conclusion is that it is in linear region. This is a contradiction, which means our original assumption was wrong. The assumption was that M1 is in saturation. If that is wrong, then the only other option is M1 is in linear region. So we can conclude that the assumption is wrong, therefore M1 is in linear region. So M1 is in linear region, M2 is in saturation. Even in this condition, drain currents are the same. So we can write ID1 is equal to ID2. The only difference is for ID1, since the MOSFET 1 is in linear region, we'll have to use the expression for drain current for a MOSFET in linear region. For ID2, we'll have to use the other expression, which is the expression for drain current of a MOSFET in saturation region, like this. So on the left hand side of the equation, we get Kn1 multiplied by VGS minus VTH of the first MOSFET multiplied by VDS of the first MOSFET minus VDS1 squared divided by 2. On the right hand side, we have half of Kn2 multiplied by VGS minus VTH of the second MOSFET squared. Now, according to the question, Kn2 is 2 times Kn1. So half of Kn2 will be equal to Kn1. That means Kn1 over here and Kn2 divided by 2 can be cancelled. Also, VGS minus VTH for the first MOSFET is 1 volt. VDS for the first MOSFET is Vx. So on the left hand side, we get 1 times Vx minus Vx square by 2. On the right hand side, VGS minus VTH of the second MOSFET is 1 minus Vx. So we get 1 minus Vx whole square. This gives us the quadratic equation 3Vx square minus 6Vx plus 2 is equal to 0. We can find Vx like this. Minus b plus or minus root of b square minus 4ac divided by 2a. This gives us two possible values of Vx. One is 0.4226. The other is 1.577. We have to find out which one is the correct value. We know for the second MOSFET, VGS minus VTH is 1 minus Vx and it should be greater than or equal to the threshold voltage. Threshold voltage according to the question is 1 volt. So 1 minus the value of Vx should be greater than 1 volt, which means Vx cannot be 1.577 volt. Vx should be 0.4226 volt. So accurate to 2 decimal places, we can say the voltage in volts is 0.423. Let's see the next problem. We have two identical NMOS transistors M1 and M2. They are connected as shown in the figure. The circuit is used as an amplifier with the input connected between gate and source terminals and the output is taken between the drain and source terminals. V bias and Vd are adjusted so that both transistors are in saturation. The transconductance of the combination is defined as the partial derivative of Id with respect to Vgs, and the output resistance is defined as the partial derivative of Vgs with respect to Id. Here Id is the current flowing into the drain of M2. GM1 and GM2 are the transconductances and RO1 and RO2 are the output resistances of the individual transistors M1 and M2. What we have to find out is which of the following statements is correct. What we basically have to find out is GM and RO of the entire connection in terms of GM1, GM2, RO1 and RO2. Let us start by marking ID over here, because according to the question, ID is the drain current flowing to the drain of the second MOSFET. I'll also mark the drain current of M1. I'll call it ID1. To find the equivalent output resistance, let us use the small signal model. First, I will take the small signal model of the transistor M2. At the gate of the second MOSFET, we have V bias. In the small signal model, it will be shorted, so the gate will be connected to the AC ground. Now, M2 has an output resistance RO2. In the small signal model, it has to be connected between the drain and source of the second MOSFET. Also, at the source of M2, we have M1. Source of M2 is connected to the drain of M1. Now, M1 is a normal MOSFET. If you look through the drain, what will be its resistance? It will be R01. So in the small signal model, we can model this MOSFET as a resistor whose value is R01. Its one end will be connected to the source of the MOSFET number 2. The other end is considered the ground. So in the small signal model, we can show it like this. You can also draw the entire small signal model of a MOSFET and connect it over here. You'll still get the same final answer. But just to make it easier, I have modeled the first MOSFET as a resistor whose resistance is R01. Now, what we are trying to find out is the total output resistance. Output is taken at the drain. So to find the output resistance, I have to connect Vx over here and find its relation with Ix, which will be the current flowing into it. Consider this node. Ix is flowing into it. GM2 VGS2 is flowing out of it. So the current flowing through RO2 will be Ix minus GM2 VGS2. Since that current is flowing in this direction, potential drop across RO2 will have positive potential here, negative here. Now at this node, these two currents combine again. Ix minus GM2 VGS2 plus GM2 VGS2 is Ix. So the current that flows through RO1 is Ix again. Also, since Ix is flowing in this direction, RO1 will have positive potential here, negative here. Let us apply Kirchhoff's voltage law in the gate source loop, which is this one. I'll start from ground. I have VGS2. I have RO1. Go back to ground. There are only two potential drops. First one is the potential drop across RO1, which will be, according to Ohm's law, Ix multiplied by RO1. If I go anti-clockwise, it is from negative to positive. There is VGS2 from negative to positive. So I can say VGS2 plus IXRO1 is equal to 0, or VGS2 is negative of IXRO1. Now let us apply Kirchhoff's voltage law in this loop. I'll start from ground. There is RO1. I reach the source. I go to RO2. And then there is Vx going back to ground. I'll start from this point and go anti-clockwise. First I have Vx from negative to positive. So I will write Vx. As I go on, I have RO2 through which a current Ix minus GM2 VGS2 is flowing. But the potential difference is from positive to negative. So I have to write negative of Ix minus GM2 VGS2 multiplied by RO2. As I further go on, I have RO1 through which a current Ix is flowing. Positive here, negative here. So I will write minus IXRO1. According to Kirchhoff's voltage law, this will be equal to 0. This gives us Vx is Ix plus GM2 IXRO1 RO2 plus IXRO1. We have Ix in all the terms on the right hand side. So that can be written as Ix multiplied by RO2 plus GM2 RO1 RO2 minus RO1. What we want is Vx by Ix. From here, we can easily write it is RO2 plus GM2RO1 RO2 plus RO1. Here, GM2 multiplied by RO1 multiplied by RO2 will be a huge value when compared with RO2 plus RO1. So we can say this is approximately equal to just GM2 RO1 RO2. Or the output resistance of the entire circuit RO is approximately equal to GM2 RO1 RO2. We also have to find out the transconductance of the entire circuit. According to the question, transconductance of the entire circuit GM is the partial derivative of ID with respect to VGS. But from the figure, you can see that ID is the same as ID1. So we can say GM is the partial derivative of ID1 with respect to VGS. Now, VGS is the gate source voltage of M1. ID1 is the drain current of M1. So when you take partial derivative of ID1 with respect to VGS, you are actually getting the transconductance of M1. So we can say transconductance of the entire circuit GM is actually equal to GM1. So the correct option is option C. Let us see the next problem. Assuming that the transistors M1 and M2 are identical and they have a threshold voltage of 1 volt, we have to find out the state of the transistors M1 and M2. Which means we have to find out if they are in saturation region or linear region. This is kind of the same as the first problem we solved, except we only have to do half of the work. We only have to figure out if the transistors are in linear region or saturation region. Let us start by calling this point as X. So the potential there will be Vx. Now consider the second MOSFET M2. Let us find an expression for VGS minus VT. Here the gate voltage is 2.5 volt. Source voltage is Vx. So VGS is 2.5 minus Vx. Threshold voltage according to the question is 1. So VGS minus VT will be 2.5 minus Vx minus 1, which is 1.5 minus Vx. Now, what will be VDS? For the second MOSFET, drain voltage is 3 volt. Source voltage is Vx. So VDS or VD minus Vx will be 3 minus Vx. Obviously, 3 minus Vx is greater than 1.5 minus Vx. So we can write VDS is greater than VGS minus VT. That means M2 is in saturation. Now, just like we saw in the first problem, it is not easy to find the state of M1 just like this. So let us start by assuming that M1 is in saturation. Again, drain current for both MOSFETs will be the same. So we can write ID1 is equal to ID2. We already know M2 is in saturation and we are assuming M1 is in saturation. So we can use the same expression for ID1 and ID2. Kn VGS minus VT for the first MOSFET squared is the same as Kn VGS minus VT for the second MOSFET squared. Kn and Kn gets cancelled because the two MOSFETs are identical. VGS minus VT for the first MOSFET. Gate is at 2, source is at 0. So VGS is 2 volt. Threshold voltage is 1. So we get 2 minus 1. VGS minus VT for the second MOSFET, it is 1.5 minus Vx. So we get this. Solving this, we get Vx is 0.5 volt. Assuming Vx is 0.5 volt, let us check the conditions for MOSFET number 1. If Vx is 0.5 volt, for MOSFET number 1, we found that VGS minus VT is 1 volt. What will be VDS? We saw VDS is Vx minus 0 or Vx. Since we are taking Vx to be 0.5, VDS is 0.5 volt. But that means VDS is less than 1 volt. Or VDS is less than VGS minus VT. That means MOSFET number 2 is in linear region, but we assumed it is in saturation region. Our conclusion is different. That means there is a contradiction and our assumption is wrong. The assumption was that M1 is in saturation. If that is wrong, then the other option is M1 is in linear region. So M1 is in linear region, M2 is in saturation region. Option C is correct. Let us see the next problem. We have an N-channel enhancement mode MOSFET. It is biased at VGS being greater than the threshold voltage and VDS is greater than VGS minus VTH, which means it is operating in the saturation region. The channel length modulation is considered significant. Then we have to figure out if the MOSFET behaves as a voltage source with zero output impedance, voltage source with non-zero output impedance, current source with finite output impedance, or current source with infinite output impedance. We can easily do that by taking the small signal model of an enhancement mode N-channel MOSFET that is in saturation region. Since channel length modulation is to be considered, we have RO between the drain and the source. Now at the output we get a current that is controlled by VGS, which is the input voltage. So when you look from here, what you see is a current source that has an output impedance. Again, option C is correct. Let us see the next problem. For the circuit given in the figure, assume that the transistor is in saturation. Its threshold voltage is 1 volt and mu n Cox W by L is 1 milliampere per volt square. Channel length modulation is neglected. Body bias effect is also neglected. What we have to find out is the drain current in milliampere. Let us figure this out. The first thing I can see is that the gate voltage is given through a voltage divider. We have 8 volt supply. It is divided between the 3 mega ohm and 5 mega ohm. Whatever is dropped across the 5 mega ohm is given to the gate. So gate voltage is 8 divided by 3 plus 5 multiplied by 5, which is equal to 5 volt. Now ID is the drain current. So it is the current that flows through RS. That means the potential drop across RS will be ID multiplied by 1 kilo ohm. And that will be our source voltage. So we can write Vs is ID multiplied by 1 or ID. Since ID is in milliamperes and RS is in kilo ohm, I can take Vs is this much volt. We got Vg, we got Vs. So let us write an expression for VGS, which is Vg minus Vs. It is 5 minus ID. So ID is 5 minus VGS. Now it is given in the question that the MOSFET is in saturation. So the drain current is given by the expression half mu n Cox W by L VGS minus VTH whole square. Now ID is 5 minus VGS, so we can write it like this. Now the value of mu n Cox W by L is given. VTH is also given. So substituting the values, we get this. 5 minus VGS is half of VGS minus 1 whole square. Solving the quadratic equation, we get the value of VGS. It is 3 volt. But ID is 5 minus VGS, so ID is 2 milliampere. The final answer is 2. Let us see the next problem. In the circuit given in the figure, transistor M1 is in saturation and it has a transconductance 0.01 Siemens. We can ignore the internal parasitic capacitances and assume that channel length modulation coefficient lambda is 0. Then we have to find the small signal input pole frequency in kilohertz. Let us start with the small signal model. There is a 1 kilo ohm between the drain and the AC ground. There is also a 5 kilo ohm between the gate and the input. Finally, we have a capacitor and that is between the drain and the gate. So we can show it over here like this. Assume that the value of capacitance is C. According to Miller's theorem, C will appear at the input as AV minus 1 multiplied by C. AV here is the gain of the circuit without C in it. It will also appear at the output as C multiplied by 1 minus 1 by AV, which will be approximately equal to C itself, like this. Now the question is to find the input Paul frequency. The input Paul frequency comes from the input RC circuit we have over here. Now before we do anything, we have to find the value of C multiplied by 1 minus AV. C is given in the question. It is 50 picofarad. What we need is AV. AV here is the gain of this circuit when the capacitance C is not included. When this is not included, all we have here is a common source amplifier. Its gain is minus GMRD. So AV is minus GMRD. It is the open loop gain of our amplifier. GM is given in the question. RD is 1 kilo ohm. So we get the gain. It is minus 10. Using this value, let us find C multiplied by 1 minus AV. It is 50 picofarad multiplied by 1 minus minus 10 or 1 plus 10. Again, what we have to find out is the input pole frequency. It comes from the input RC circuit we have over here. Pole frequency of the RC circuit will be 1 by 2 pi RC. R is 5 kilo ohm. C is C multiplied by 1 minus AV. Substituting the values, this is what we get. The pole frequency is 57.87 kilohertz. So the final answer is 57.87. Let us see the next problem. In the circuit shown in the figure, the channel length modulation of all the transistors is non-zero. Also, all transistors operate in saturation region and they have negligible body effect. What we have to find out is the AC small signal voltage gain of the circuit. Let us see how we can do this. The first thing we need, as always, is the small signal model. I'll start by taking the small signal model of MOSFET number 1. Input is given at the gate of the first MOSFET. So we can show it over here. Its source is grounded. Since channel length modulation has to be considered for all MOSFETs, we'll connect RO1 between the drain and the source. Output is taken at the drain, so let us also show that. Now VDD is given together to M2 and M3. Let us show it separately like this. So it is such that at the drain of MOSFET 1, we have MOSFET 2 and MOSFET 3. Now, is MOSFET 2 familiar to you? Its drain and gate are connected, which means it is a diode connected MOSFET. A diode connected MOSFET can be modeled as a resistor whose resistance is 1 by transconductance. But there is a slight difference here. We also have to consider the channel length modulation in M2. So M2 is basically a resistor whose resistance is 1 by transconductance with RO2 in parallel to it. If you draw the small signal model of M2, at the output you will also have RO2. So considering channel length modulation, this whole thing over here can be modeled as a resistor whose value is 1 by GM2 parallel to RO2. It will be connected between the drain of MOSFET 1 and the AC ground, like this. Now let us see M3. I'll take the small signal model of M3. Its drain will be connected to the drain of M1. One important thing to note here is that M3 is a PNP transistor. So the direction of GM VGS will be opposite. Direction of VGS will also be opposite. So I will draw its small signal model with the source on top and gate and drain at the bottom, like this. You can see that the direction of current is from source to drain, which is opposite to what we have over here. Here it is drain to source. VGS3 has positive potential at the source, negative at the gate, which is also opposite. For example, over here in the small signal model of an N MOSFET, VGS has positive potential at the gain and negative at the source. Anyways, their drains are connected just like it is over here in the circuit. Again, for M3 also we have to consider channel length modulation. So we will have RO3 between the drain and the source. So we will have RO3 connected between the source and drain of M3. Now at the gate of M3 we have VG. It will get shorted. So gate will be grounded. At the source we have VDD. So source will also go to the AC ground. Now take a look at VGS3. This end is at the ground. This end is also at the ground. So basically the potential difference between these 2 points is 0. That means VGS3 is 0. If VGS3 is 0, then GM-VGS3 is also 0. Take a look at RO3. It has 0 potential on this end and VO on this end. So it has positive potential here and negative potential here. That means a current will flow through RO3 in this direction. Now current across RO3, which has a potential VO across it, will be VO divided by RO3. Since this current is 0, VO by RO3 must have flowed like this. So over here, let us show the current VO divided by RO3. Now take a look at 1 by GM2 parallel to RO2. It gets VO potential here, 0 potential here. So a current will flow through it in this direction, giving positive potential here and negative here. And that current will be equal to VO divided by 1 by GM2 parallel to RO2. Let us show it over here. Now take a look at RO1. It has a potential VO over here and 0 over here. So a current will flow through it like this, giving positive potential here and negative here. And the current will be equal to VO divided by RO1. Now VO by RO1 flows like this and GM1 VGS1 flows like this. So the total current flowing in this branch is GM1 VGS1 plus VO by RO1. Let us show it over there. Finally, take a look at this node. There are 3 currents. VO by RO3 going out. VO by 1 by GM2 parallel to RO2 going out. GM VGS1 plus Vx by RO1 also going out. According to Kirchhoff's current law, the sum of all these 3 currents should be equal to 0. We have VGS1 in this equation. Take a look at the input of MOSFET number 1. Vin is given between the gate and source. So VGS1 is equal to input voltage. So we can modify the equation like this. GM1 Vin plus VO by RO1 plus VO by RO3 plus VO by 1 by GM2 parallel to RO2 is equal to 0. Or we can write GM1 Vin is negative of VO multiplied by 1 by RO1 plus 1 by RO3 plus 1 by GM2 parallel to RO2. What we have to find out is the voltage gain, which is VO divided by Vin. From this equation, we can easily write it. It is minus GM1 multiplied by 1 divided by this whole thing. Now, what we have over here is of the form 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3. This is the same as R1 parallel to R2 parallel to R3. So we can write the gain like this. It is minus G1 multiplied by RO1 parallel to RO3 parallel to 1 by GM2 parallel to RO2. Option C is once again the correct answer. Now, you must be thinking, how do I do all of this work in a limited amount of time? The good news is you don't have to. In competitive exams with limited time, you will never get a problem that takes 30-40 minutes to solve. There is always a better way. And obviously, I'll teach you that. First, let us give VDD separately to M2 and M3 so that we can consider them as separate modules. Now, we already said M2 is a diode connected MOSFET and channel length modulation is included. So it can be modeled as a resistor whose resistance is 1 by GM2 parallel to RO2. Take a look at M1. Input is given at the gate of M1. Output is taken at the drain of M1. So basically what we have over here is a common source amplifier. At the drain of the common source amplifier, we have M2 and M3. We already saw that M2 is a diode connected transistor, so it can be modeled as a resistor whose resistance is 1 by GM2 parallel to RO2 because channel length modulation is also included. Now, how about M3? This is also connected between the drain of the common source amplifier and the supply VDD. In fact, drain of M3 is connected. Now M3 does not have any resistors connected to it, but channel length modulation is included. So if you draw the small signal model, all you will have at the drain is the output resistance RO3. So we can model this much of the circuit as a resistor whose resistance is RO3. It will be connected between the drain of MOSFET number 1 and the AC ground. We can model the circuit like this. Now what we have is a simple common source amplifier who has RO3 parallel to 1 by GM2 parallel to RO2 at the drain. If we draw the small signal model, this is how it will look like. Since channel length modulation of M1 is to be included, we have RO1 from its drain to the source. Now there will be RO3 from the drain to the AC ground. We will also have 1 by GM2 parallel to RO2 from drain to the AC ground. Well, we don't even need the small signal model here because basically what you have over here is a common source amplifier. And the gain of a common source amplifier is minus GM RD. RD is the equivalent resistance you have at the drain. From the circuit, we can see that the equivalent resistance we have at the drain is RO3 parallel to 1 by GM2 parallel to RO2. So the gain is minus GM multiplied by that. Again, option C is the correct answer. If it were that easy, why did I do this whole thing first? I just wanted to prove to you that my technique is correct. Also, I guess I wanted to show off a little bit. Spare me for that. Let us see the final problem. In the circuit, both the enhancement mode NMOS transistors have the following characteristics. Kn, which is mu n Cox W by L, is 1 milliampere per volt square. Threshold voltage for the N MOSFET is 1 volt. We can assume that the channel length modulation parameter is 0. Body is shorted to the source, which means body effect is also not to be considered. What we have to find out is the minimum supply voltage in volts needed to ensure that the transistor M1 operates in saturation mode. Let us see how we can do this. Let us start by calling this point X. So the potential there is Vx. We have to find out VDD so that both transistors are in saturation. Let us start with M1. M1 is in saturation. That means VDS1 is greater than or equal to VGS1 minus VTH1. What is VDS1? For M1, drain voltage is Vx. Source voltage is 0. So VDS1 is Vx minus 0 or Vx. What is VGS1? Vg is 2 volt, Vs is 0. So VGS1 is 2 minus 0. Threshold voltage is given in the question, it is 1 volt. So we can write Vx minus 0 is greater than or equal to 2 minus 0 minus 1. Or Vx is greater than or equal to 1 volt. So Vx over here can take values that is greater than 1 volt. But we need to find out the minimum possible value of VDD. For minimum possible value of VDD, Vx will take its minimum possible value, which is 1 volt. So let us take the value of Vx as 1 volt. Now the drain current of MOSFET 2 is the same as the drain current of MOSFET 1. ID1 is equal to ID2. Since they are both in saturation, we can use the same expression for ID1 and ID2. Half mu n Cox W by L VGS minus VTH whole square. So we can write it like this. Transistors are identical, so half Kn and half Kn will get cancelled. VGS1 is 2 volt, VT is 1 volt. What is VGS2? M2 has a gate voltage that is equal to VDD. Its source voltage is Vx. So VGS2 is VDD minus Vx. Again we have Vt, which is 1 volt. So giving the values, this is what we get. Now for minimum VDD, Vx has to be 1 volt. So over here, Vx can be replaced with 1 volt, and that gives us the minimum value of VDD required for both transistors to be in saturation, and it is 3 volt. So that's all about it for today. See you in the next video, and please don't forget to subscribe.